Thank you very much. It's a surprise to hear all this information in a very short time, even though we've had it. My daughter had typed it out. To begin with, I want to point out that a lot of your own electricity in this country comes actually from Canada. And we have the James Bay project up here called G1 and G2. Robert Bourassa, the Quebec leader, had envisioned to tap into the hydro and send it with a high voltage power line into New York. And so it was anticipated, the line is actually 167 volts. It's a state of the art. Quebec Hydro is it's a Crown corporation, and there's a fair amount of return on investment coming in. And so there was further need for the electrical energy, and all of a sudden, Robert Bourassa decided, let's go into phase 2 of the project. So they started to get the native people, land claim issues settled. And so all of a sudden we had the compact fluorescent light, and the energy consumption was reduced. So phase 2 of the project of James Bay never occurred. So the native people were very happy about that particular development. A long time ago, and I read it in the National Geographic, there's an electrical engineer, and I don't have his name on hand, but many of the other ones I have. And this is a superconductor. It's cooled down to 271.25 degrees. 1,150 tons of helium is used to cool the line. And so when you have a copper conductor with that low temperature, there's no resistance and no energy losses. So this line would feed New York, the entire line. Normally it would be many overhead transmission lines, many conductors on one unit. And so this is a brand new achievement for taking energy over long distances without losses. There's a gentleman in Holland, Van de Graaf, who had designed a spear and a tower where high voltage is being produced. And in order to do that, there's a hand crank and a belt which will go from the top to the, and then if an electrical motor can turn it, and as a result of these two brushes, it can produce about 1.5 million volts at very little amperage. So that was a Van de Graaf accelerator. And there's one in Edmonton, Alberta, at our university. It's located at our university. It's a nuclear physics research lab. High voltage are required for many tests, many installations of electrical lines for long distance. Here's the Hudson Bay in Canada. Manitoba's here with the town of Winnipeg. And there's the Kettle Rapids on the Nelson River. And high voltage is transferred from the dam into Winnipeg. It's a single conductor line, 1 million volts, and the earth is the ground. And there's a converter station in Dorset, which is about 20 kilometers away from Winnipeg, or 17 kilometers, and it turns the DC into three-phase AC power. So it's a fairly long line, over 750 kilometers, single conductor. The price of copper right now is over $8,000 a ton, $8,580, or $5.60 a pound. So you can save on copper wires a great deal by going on that path of higher voltages. Let me see if I have a high voltage electrical tower here. You're all familiar with those towers. We see them everywhere in Ashland. Or at the high voltage substation here on Mountain Avenue. Some time ago, that was in 1772, there was Samuel Hearn. There was a Hudson Bay Company post in the Hudson Bay, and here's Greenland. And this represents the Arctic Circle. Here's the three provinces, Alberta. Anyway, Canada actually began with the Hudson Bay Company in 2nd of May, 1670. And at Fort Prince of Wales, at the mouth of the Churchill River, was a post. And Samuel Hearn, here's the photo I have of him. That's the best one I have at the moment. We could not find the time to have it Xerox, but that was what he looked like in 1771. He was the Hudson Bay governor at that time, and it was the Hudson Bay Company received a charter to obtain furs from the native people. And so it was a trading post well before Lewis and Clark was actually busy doing his part. So the managers of the Hudson Bay Company had asked, why don't you go and look around and see what all the water flowing into the Hudson Bay, literally the drainage system was then the Hudson Bay Territory, which was chartered given by Prince Rupert. So let's find out what's beyond our drainage system. And so Samuel Hearn in 1771 started on a journey and on snowshoes trying to find the Arctic Ocean. The idea was of a northwest passage at one time, so to get maybe to China. So 2 of these attempts failed, and the last one, the chief called Manitoba, Manitobi was his name. He agreed that he would make his native people available. So there were 250 native Indians, including the husbands, the wives, and the kids. And the journey took him almost 2 years to go from Fort Prince of Wales at the Churchill River all the way to the Copper Mine River in this direction, and it was a long journey. So by taking all the native people with him, he had literally everything what you can find at Walmart: food, clothing, family at the same time, tools. And so the hunters would go out and get all kinds of animals, deers, to support each other during the trip. And very successful, he found the way to the ocean, and he took out his chemical test. And that was just the tongue, and test the water, and that was salt water, that was the ocean. So he was very happy with it. And on this way, in this area at Copper Mine River, he found a lump of copper, 8 pounds in weight, native copper as we call it. What you have to understand too is that native people lived in that area for a long period of time. We were already finished with the Stone Age, the Copper Age, the Bronze Age, the Iron Age, and the native people were still in the Copper Age, literally. So copper was used by them for the benefit of making all kinds of implements and tools. So anyway, we use copper in our own trade for the conduction of electrical energy. Long time ago, I will go back to the 15th century. William Gilbert, Professor William Gilbert here on this photo, was interested in electricity, but he did not really knew it was electricity. It was static electricity. And so in the 15th century, he was experimenting with it, and he used something similar to a Van de Graaff accelerator, or when you walk in your room around the house on a very dry day and you touch the doorknob after you walk over a rock, you get a little electrical shock. It's called static electricity. He entertained the Queen Elizabeth I. All kinds of fancy engagements were made, and he made a living at it by just engaging the royalties with his entertainment. So what he had learned from it was, what we have learned is there was static electricity. And maybe I should point out to you that there's more than one way to make electricity. This particular unit here, so I use them. These are 2 thermocouples. And if I put a match underneath, it produces an electrical current, and it will register on the instrument. because they're two dissimilar metals, and when they're bonded together and heated, gives electricity. So that's another form of electrical energy generated by using thermocouples called Seebeck effect. The other method would be, and there's a second one available, and there's a third one as well. This is the magnetic one. It's called electromotive force. So here's a magnet in my hand, and there's the instrument. So when I put this magnet into this coil, it shows a reading. There we are. There's a little bit activity. So I could stay here all day and make electric power by sending a magnet through a coil. It's called through induction that I make electric power by going in and out. And I will get hungry after a while, and there would be nothing electrical produced, so I let the wind generator do it. Let's see what happened. There, the wind can do it. So there is another form by using a magnet and an electrical coil to make electricity, and you have learned now the third kind of electrical energy production. Benjamin Franklin he lived from 1706 to 1790, and he worked with a kite long time ago, and there was also a certain amount of confusion as to what was going to happen. There's another form of electricity, and they didn't know really what to do with all it. There were so many different approaches of producing. Can they all be part of the same thing? And the question was raised, maybe not. In Italy, at the university in Bologna, there was Louis Galvani. And he was a professor there, and for many years he was teaching taking frogs apart, etc. And he used tools to emphasize by separating the meat from the bones, etc. And all of a sudden, while he was doing this job, the lake started to move. So he called it electrical energy, animal energy. So now all of a sudden we had a new kind. So he was very much perplexed, 1737 to 1798. So he wrote a letter to Ampere in France and asked the question of what was happening. I find animal electricity. And this document is still around to this day. And Ampere is explaining it in full detail as to what is actually happening. There he is. He's a Frenchman. Electrical current is named after him, as you might remember. Marie-André. And so he was satisfied with the answer. That is Louis Galvani. All of a sudden, something happened in Denmark. Hans Ørsted is his name, and there he is. He was a professor at the local university, and he was, that's him right here. He was teaching at the university about electricity in the lab. And so all of a sudden, while he was teaching it, there was a compass needle nearby, and electrical current was going through the conductor, and all of a sudden the compass needle started to fluctuate. How is this possible? Anyway, there it is. It's a medallion now issued by the Copenhagen government. There's another one. And so there are now so much confusion occurring with what is right and what is wrong, not necessarily wrong. Are these all different kinds of electrical energy? Of course, I'm just jumping the gun. Edison had worked on direct current for a long period of time, and Tesla on AC, which came much later. As it occurs, there was a confusion as to what should we do. And in the end, it was agreed that the various physicists which existed, that is Watt, Ampere, Coulomb, Faraday, Volta, Georg Simon Ohm, Joule, and Henry. They got together, and it works out that a document was filed in the House of Commons in Ottawa sometime in the year of 1894 on June, and it was a bill 117. And Canada, as you know, was already a dominion by then. And so many of the issues which were passed in Parliament came actually from England through the British North America Act. So immediately a bill went into the House with these issues of the ohm, the volt, and the watt, and it was agreed on one specific day that this we need to pass a bill. There is more, if you use electrical energy, you need to charge for the electric energy. And how do we do it? So with watt and watt-hour meters, there was a whole series of intellectual people who submitted their input, and eventually these units were agreed in principle. 1 year it took before the United States adopted the very same units, the ampere, the ohm, the volt, and the watt, and it occurred in May 1895 under the House Record 4000. And so the lines are given here, and vertical lines are given in yellow and in green. Now, what I wanted to emphasize is when Ørsted made his experiment in the lab in Copenhagen, and he found out that there was an electrical magnetic field occurred in the wire, and the compass needle moved. So I drew a line there in 1820. In 1820, you'll find out in the bar graph what the age of the various physicists was at the time. So what we can see in it, James Watt was almost at the end of his life when that particular act was passed. And others, their life began, like Joule as an example. So there's the combined one-line diagram indicating the technique. So I read the House Record 4000, and there was a gentleman in the cabinet who said, of course, when the bill is introduced in the House, there's question periods. It goes through 3 stages before it's adopted. And one of the gentlemen got up and he says, this is all sort of like hogwash. I know what a bushel is. I don't need to know the rest. What I like to say with that particular instrument, we have now moved much further ahead. We now know what an ohm is, an ampere, and a volt, etc. But when you have elected representative making a statement like that, I don't need to know that, I know what a bushel is. Perhaps it could be translated into today's method at the same time, when you have politicians in Ottawa who really don't care. They're elected, they get paid, and then they don't represent you in a way which should be responsible. So what I had done is I put these various physicists together, and in Edmonton, when the 100th anniversary came along in 1994, we had a get-together at our high school, and the Minister of Industry from Ottawa came to us, and so we were kind of congratulated about us, what we have done. So there is a little unit I had designed on my own. Here's Georg Simon Ohm, the resistor. I have a nice portrait of him. And here's Joule also. 1 joule is the amount of current of 1 ampere going through a conductor in 1 second. And this is Coulomb, very very fancy looking individuals in their clothing, I should say. Thank you, Sid. So I will go back once more to this area here in Canada when Samuel Hearne, the first picture I showed, had traveled from Fort Prince of Wales to the Coppermine River. Well, it was put on hold because he came back with a pound or lump of copper, which is in London today, and it has not returned back to Canada, 8 pounds. And so George Douglas from the United States, a geologist, came along, and he said, you know, we'd like to know more about what's happening. So in 1911, he traveled from the US and came up, traveled on the Nelson River, and then worked its way through the Ceylon Game Sanctuary, past Great Slave Lake, Great Bear Lake, into the area where the copper was found. And the final outcome was there isn't really very much in the way of mining to be done in this particular field. That's George Douglas right here in 1911. It's a special drawing. So when we have all kinds of electrical currents, you need watt-hour meters, you need voltmeter, you need ampere meters. So here's a Frenchman, d'Arsenval. I got that directly from Paris. He, if you have an electrical instrument, very much like a clock it is, it's got very fine electrical wires in it, and it has a bearing on the top and one on the bottom, and it is usually a jewel on the bottom, one on the top, and a spring. And so when electrical current goes through this coil, it has a movement. So d'Arsenval in France designed it, and to this day we have very fancy instruments which show the amount of electrical current. Anyway, there are measuring instruments. I should have brought one with me. You saw one over here. It's a zero reading in a second in the center, and then left is positive, and the other one is negative. And in the center is where the pivot is, and the spring is located. So there's a very electrical instruments, other than the brand new ones we have. They're digitalized fluke instruments. They just go on chips, while here you can't haul them around all the time. They get damaged, so you have to be careful. Some actually have a special switch that you can lock the needle and protect it from happening. So d'Arsenval was not an industrialist to mass-producing instrument. It was Dr. Edward Weston, and he was from the United States, and all the best instruments are made by Dr. Edward Weston. We will talk about Edison for a while. Before Edison invented the light bulb, he actually had two carbon rods, and when they held together, they create an arc, and then you have a light, which was about 15 years before the incandescent light bulb was invented. So you have a screw of an adjustment, and as the flame comes, you have to constantly keep feeding the carbon rod closer together to make the flame, to keep the flame going. And they're very bright, very brilliant. So here's a little picture of Thomas Edison. Edison was a very strong-minded individual. He believed in direct current, and he would not go for alternating current. Matter of fact, it was Tesla who was eventually hired by Edison, and they shared the same lab. And so there was a bit of a clash as to what would be winning. When you're dealing with DC current, you have a lot of voltage drop, and Edison's methodology was to have a generator producing electric power for each of the buildings in New York. And Tesla would say, we can do an AC system that keeps feeding several buildings, and we have a watt-hour meter, which Westinghouse had invented at that time, and there would be no problem. Edison could only register 5 amperes at the most, and it was a liquid in the watt-hour meter. There was a liquid involved, and then he would weigh the liquid to find out how many kilowatt hours of energy was used. So it was a very slow process. So it's best to put it on the back burner. And in the long run, Tesla won. I have this gentleman's name here, Oliver Thomson, who invented the conventional watt-hour meter as we have them today. He only lived to be 38 years of age, but he started to experiment with the three-phase watt-hour meter between 1860 and 1898. That's Oliver right here. Along the lines we had, there was so much electrical energy, we better do a kind of a world show like they have in Chicago or in New Orleans. Sid and I, a friend to New Orleans, and we traveled there with a car, and we took a ride in the cable car across the Mississippi. It was a beautiful thing. It's a place to show off, to really be proud of. We had the World Fair in Canada at Montreal in 1867, I believe it was, 1972. And so there was a great big one in 1894 in Chicago, and it was a light festival right there where many of the items were shown, electric light, electric motors. It was a complete new system. Industrialists had come forward manufacturing various things. So we have a German inventor, Werner von Siemens, who had two other brothers. One was working out of Berlin, where I was born, and Siemens. And he had another brother who was working out of London, having a factory, and another one in Petersburg. And the first part of what they were doing was building actually submarine cables for communication. And I have a little diagram here showing what in I believe it was in 1858, underground cables from London to New York or to South America, Rio de Janeiro. Sid and I were at the World Fair, at the World Environment in 1992 in Rio de Janeiro. Anyway, it's showing all the underground cables, interconnecting the continents with the communication line. So Werner von Siemens was an industrialist, and he also built electric motors and dynamos to make electric power. Here's another colored photo of him in his earlier years. Siemens was very careful. When he spliced the cables, he used this particularly is the device. It's a testing device. It's a glass tube filled with mercury. It's exactly 1 ohm. And when he tested each cable which needed to be spliced as the ships were crossing the ocean, he knew exactly what the resistance was of each. And when the splices were made, it proved that they were correct. And at the same time, $58,000 we made available from the American government for a cable to run from England to London, from London to New York. And it failed. They just spliced it, and later on when they made the test, it didn't work. So they had to go back for more money, and the government was very unhappy. So I just want to show to you that when you do make your tests ahead of time or during the time, rather than assuming that everything is right. He used gutta percha. It's an isolating material. Nowadays, it could be considered perhaps as nylon or other materials. It starts with Sid. Maybe you could help me. The people in South America are there boiling. Latex, that's it. Latex is also a very good insulator, but gutta percha was what the Siemens Corporation used for the insulating material between the conductors. Another thing what has occurred, electrical energy, in order to test an instrument, to be sure that after it's been moved around from one place to another, sometimes get damaged and the reading you make is inaccurate. So here's a good item to test it against. It's called a standard cell. There's mercury in the bottom, a dielectric in the top, and it has a current flow, positive and negative, and it will last for years and years and years without, and then it is 1.2 volts, and then you take that instrument and then test it against your electrical units, and then it can be verified that it's still in good working condition. So this is a very standard practice for testing your instruments against it. Long time ago, there was a gentleman by the name of Steinmetz who was the chief electrical engineer for General Electric, and he was a wizard. He developed all kinds of interesting things, and one of the units he had worked with was to make out of alternating current DC, which was called a rectifier. And here's this rectifier which he had designed. There's mercury in the bottom, and the electrodes of current go through it, and then alternating current is added, and then in the end it becomes DC using mercury, which is a kind of a poison. But anyway, it was successful. The mercury rectifier has been put aside, and it's been replaced with a modern silicon rectifier. And here's just a drawing of a modern silicon rectifier. I have the technologies here with me as to how it works in principle. There's a modernized mercury rectifier. Alternating current is added in the top in a laminated iron core, and then the wires go down to the bottom. There's a small DC battery, and you have to start it with an electrical current, and then ultimately the DC will flow. So it's not just putting in energy and getting it out. It's a technique which is essential. And now we have electric cars which require electrical current for the battery, and it is a silicon rectifier which does it. But in the early stages, in fact, in the town of Berlin where I lived, they had electric streetcars, they had electric buses. 1905, there were more electric cars on the road than there are internal combustion engines. So they used mercury to make DC out of alternating current. And so that was the... I beg your pardon? 1913. 1913, there were more electric cars on the road than there were internal combustion engines.
In New York City also.
Yeah, worldwide for that matter, not just in Berlin itself. Steinmetz was a very interesting character. He worked together with Edison a great deal. And there was Ford Motor, Henry Ford, came to Steinmetz, you know, I have this Model T Ford and I drive it, and the light would be nice and shiny when I drive on the road, and when the engine is idling, the light is so dim, and I wonder if there's some improvements we can make along the way. So here they are tinkering around with it, and apparently it took 20 minutes, and the bottom line was, Steinmetz says, what you need is a battery, and of course you need a voltage regulator, and then the energy from the generator goes into the battery, and it maintains the voltage using the voltage regulator. It's a gift of mankind from one person to another without charging a royalty through a patent. So I just want to emphasize, there was a time when we helped each other rather than having a handout and getting a good feedback. And it shows you also that the characters we have among Steinmetz. There's a second one here. Folks can have a look at it. You can see by the picture they're really dedicated toward their project. I wish that we have young people entering in the electrical or in the plumbing and take their job serious and become an apprentice ultimately, and put their cell phone aside and become engaged in doing something for the country. This is Nikola Tesla. He was actually born in Yugoslavia, and he came to America and patented a whole variety of items, three-phase motors, electric lighting, transformers, very outstanding. And his financier was J.P. Morgan and Westinghouse. So all kinds of equipment. When Tesla went out of business and he went into bankruptcy, I had a look at some of the equipment he had. It was amazing. Hundreds and hundreds of motors and horsepower, transformers, a whole variety of items which we wouldn't normally think of, which the company had used for his experiments. I'll just switch a little bit to another World Fair. Amazing that we have the sun out here, which can do all kinds of benefits for us to grow food through photosynthesis, provide light and heat. And here's an example as to what can be done. A friend of mine from Austria gave me a book on renewable energy, and Rudi Hinteregger was his name, and his brother was a senator in the Austrian government in Vienna. So what we have here is a large reflector where the sun can shine onto it, making steam, running a steam boiler, and then over here it runs a printing press. And this energy comes from the sun free of charge. And this was happening already in the 18th century, long time ago when there was a World Fair in progress. I'll switch the subject a little bit, and I'll talk about the high cost of wax for a moment. What we see here is Frederick the Great, 1712 to 1768, and they're smoking in this room a great deal of the time. And he was also a good flute player, very a good humanitarian. And they had music, art, literature, anything like that. It was non-destructive to the environment, and the children are saying goodbye to him. And after they left and go to bed, and after they're finished having their smoking session, he went outside to walk from the smoking room down to his apartment. And the house had an overhang with pillars, keep I guess the sunshine out during the daytime or the rain. And as he walked along, there was several candles shining at that time so that he wouldn't trip. Royalties are pampered one way or another. And he blew them, there were 5 of them, and he blew 3 of them out because there was a full moon. And the answer was, wax is expensive. So my way of thinking would be, I translated from 1750s into modern time. When we have full moon, our street lighting should be half. Would be nice. In Berlin, when I was living there, cars don't have to have their headlights on in the city because there's enough street lights. So you can save a little bit on the energy by not letting, because every time when your headlight is on, that energy comes from the gasoline that's in the tank. So the reality is, it began in Canada too, and in Sweden, where you have to have your car running with the headlights on. That is some people say, oh, well, the engine is running anyway. No, if you do the calculation, you work out that that amount of energy comes from the gas. Same thing when you look up in the sky and you see an airplane with the headlights on just before the landing. The question you should raise, how long do you think that light is going to shine? Till the tank is empty, isn't it? And that's the same thing with planet Earth. How long will our light shine on planet Earth? It's up to us to make it, to conserve. Anyway, there's Frederick the Great in the 17th century conserving on wax, which he considered to be important to be saved. When electrical wires are being spliced, you got to make sure that the connections is right. And nowadays we use a special kind of compound in the splice. It's called, help me out on that one, Sid. It's an conductive grease is added to make a splice. But that's not all. The splice has to be made just right. So when I read, because I have my own private business since 1968, we have the Canadian Electrical Code, and in Canada and the United States we have the National Electrical Code. And it's very specific. Every item is spelled out exactly how to wire it up. And when I go through to the code book, And every 5 years, every 3 years, I have to rewrite my master to be sure that I can take out permits. They're very careful in Canada too. So you study, the book is about this thick nowadays, the electrical code book. And so when I went through the various portions of the electrical code dealing with connections, it says the wiring splice has to be made secure. It has to be made strong, has to make last. And I thought, that's not enough. So what I did is I wrote a letter to the Provincial Code Committee. It's called the Alberta Advisory Committee, and I sent in the letter. I see it here, it's 1986. Our little company sent in a recommendation, and I read the first line here. Section 26, installation of electrical equipment. There are rules 10, 866, blah, 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 5 or 6 different kinds. The purpose of my letter was that what we need to do, and this is actually spelled out here, that the splice has to be made proper with so many foot-pounds in your country. For us, it's in kilopascals. When you have a bolt a certain size, you use a torque wrench to tighten up the nut. So I made the recommendation. It was approved by the Code Committee in the Quarterly Bulletin. And from now on, electricians have a torque wrench in their toolbox, not just a pair of pliers and a sight cutter and a wire stripper, but a torque wrench. So when the circuit breakers are installed stuck, you torque it down with the correct specifications. So we got some brownie points as a result of that. So that 1968, and I submitted it to the Electrical Code Committee, and it was approved. So there's something you can do as an individual, either a corporation or we're 10 minutes to 8. So I will continue a little bit, and then we can have a break, a question period, or like a social, and then the question period will come much later. Electrical energy is not only made with the methods of electric energy by using a dynamo or the heat through the Seebeck system. We also have, and here's a nice photo of the Hoover Dam. Right here where it's on the Colorado River. A nice example. Canada has quite a few. I should also point out in British Columbia, right about here, there's the Columbia River, which produces electric power, and it feeds into the Western American grid. And then there's the central, and then there's the eastern. So this particular section, quite a bit of our Columbia River, which goes down eventually through between the state of Washington and the state of Oregon. There's hydroelectric installation that's over 21,000 gigawatt of energy on the grid. It's an enormous amount of energy which is being produced by using renewable energy rather than burning coal. And right now, worldwide, even in Germany, lots of coal is still used for making electric power. In 1986, we had in Alberta a Solar Olympics, which was open to the public, and at that time, all kinds of ideas could be presented to the group or the club about renewable energy, like photovoltaic cell or wind power. And so what I did here, there's my company vehicle. In 1982, there's a wheel in the center on the back of my truck, and it's called a dynamo. German bicycles don't have a dynamo to make electric light when it puts the pressure onto the tire, but you can also have it inside the hub itself. The magnets are inside and the coils. And so if, in my case, I left the tire in there and I added steel blades, tin blades, and the wind will make it turn. So I had 6 volts and 3 watts of electrical energy, and I made a few brownie points as a result of that. 15 years later, I raised, and you heard it through my introduction, I raised $1.5 million. My son is right here too. And we put an industrial wind turbine on the grid with 65 shareholders, limited shareholders. And we poured some concrete. So these are the various stages. That's the crew we had involved by pouring the concrete. and erecting our own wind turbine tower. I'll show you. That's the wind turbine we finished right here. Produces enough energy for 860 households on a yearly basis. Costs us $1.2 million. And it's our Volvo station wagon running on diesel. It's a diesel Volvo, but running on vegetable oil. Okay, that's a Lagerway. It's a gearless machine. It's made in Netherlands. Okay, the site which we obtained in order to put this wind turbine on had the French design on it. The Savonius wind turbines were on the property. They were 1.5 megawatts. And this is the bottom where the generator is located. These are aluminum blades, 55 yards in length. And you can climb the tower to maintain it. And on the bottom is a generator, it's about 10% of the energy output of our three-bladed generator over there. That's a little close-up of all the structural engineering design. And eventually it was sort of phased out, and we installed vertical axis wind turbines on the job site. Here's another example as to how many wind turbines farms you can have in one area without air interference. We obtained a contract with the federal government through the military, and what the American government in Canada maintained a dew line for a long period of time so that early warning messages from Russia, if satellites come in, not satellites, but bombs, whatever else you call it, cruise missiles, that our American friends would have knowledge as to when they are arriving. And so we had over 50 stations at Cold Lake in Canada. And each one had a very large battery, the size of this chair area, and made the electronics work, functioning. And so the maintenance staff from the federal government has to go around to maintain these diesel generators. So there's a lot of traveling involved. So they ask us, what can we do? We want to improve the system. And so what we recommended, and we had a meeting with them, we can install photovoltaic equipment on those dog houses where the alternates are. And here we're putting up the structural steel for it. And we put up 5 kilowatts for each of those projects, and there were over 45 stations. And so the diesel assist was getting its energy from the photovoltaic cells, and they hardly ever used any more gasoline or diesel as a result of the improvement by taking energy from the sun. So when I spoke to staff here in Ashland, where we have the, I guess it's called, there's a military base out here, which the armory. They said that the US government is buying an awful lot of photovoltaic equipment. And he said the reason we're doing that is if our men out in the field have to go obtain a gallon of gas or gasoline and travel from point A to there, they could die on the way because of the enemies in the way. So if we get more energy from the sun, we don't have to purchase and make extra travels. So over a period of time, the federal government in Canada and the US are having saved a lot of fuel over time and lives by using photovoltaic equipment, and they're very strong on it. So Cold Lake in Canada has gone not necessarily overboard, but it's a fringe benefit for mankind for the security of its own country. Oh yeah, I mentioned earlier that this is the electric Baker car, which was running already in 1930 and 13, and on the roof is a photovoltaic cell. So literally it's self-sufficient by having its own energy, collecting it from the sun when the unit is parked in the parking lot, and then you can drive it. 1913, and there, as I say, there were more cars on the road, electric vis-a-vis internal combustion engine. Here's an interesting photo which I took when I came out from Edmonton, Alberta to Ashland, and I've been doing it now for 45 years. We have a little house on Oak Street. Sid and I and our granddaughter and our other 2 children come here during the winter time when it's ice cold up north. And so when I was at Umatilla, there was a truck on the road, and they're hauling a blade. So if you ever go down on the Columbia River, you see thousands and thousands of wind turbines. And that is not only, it's been done for the point of renewable energy and also assisting getting electric power rather than hydropower. So it's amazing. At times they shut them down. There's not necessarily a clash, but there's perhaps an overproduction. And so every once in a while, when you travel past, some of them are not turning or revolving. So we had a little group here in Alberta, in Ashland, I should say, Green Energy Wind Power Incorporated, of which Susie of the Heide was the chairman. And we had about anemometer stations in the valley here. We had 5, and this is one of them on Green Springs. Is it? Yeah. Yeah. It's 7 meters high or 8 yards with an anemometer and a data logger on the bottom, battery-operated photovoltaic cell. And we collect wind data on right here in White City and Ashland area. And we were quite happy with the final results. But not sufficient that we could actually install a wind turbine farm in this area. We communicated with the city of Ashland, and they're not paying too much attention. Photovoltaic is a good thing in Alberta, in the city of Ashland, and I think True South is doing a very good job. Their methodology for collecting the fees, it's incredible. It's no one else makes it the way they do it. In fact, they install the equipment, and the customer doesn't have to pay it for it, and they get the electrical energy more or less free, and that pays for the equipment. Not far on the hillside, there's a vineyard, and there's a 25 watt, 2.5 kilowatt freestanding tower. It's behind Dead Indian Memorial Road and also Mountain Avenue. I took that picture about 4 or 5 years ago. So there is wind energy in the valley, and there were some vertical axis wind turbines further up when you enter on the off ramp going on I-5. Here's a nice photo of the vertical axis wind turbine in Pincher Creek, which we maintained. There were 10 units freestanding up there, and it's a French design. Savonius is the French name for this type of equipment. I will check around and see if I can find a little bit more. Here's Tesla. Did I say Tesla? Nikola Tesla. That's it. It's an anniversary card. Beautiful, nice color. I like teaching. I like introducing the subject. Yeah. I'm not selling anything myself, but from my perspective, it's just a gift back to mankind again, you know. I have the time.
I would ask a basic question that maybe should be recorded. What exactly is electricity?
Well, it's a movement of electrons. If you have a wire and you're sending energy through it, one molecule is pushing the other molecule. They're not moving. It's a continuation of the electrons from one to the other. Electricity is, it's not like water in a way. It is, the wire cannot hold the energy. You have to unload it. And you can only allow so many kilowatt of energy going through. And if you are increasing it, then the copper wire has to increase in physical size if you want to push more through the wire. And then it could become a fire hazard. And so we put fuses or breakers in it to protect the wire. So what is electricity? Electricity is the movement of electrons in the wire. I had asked an engineer a long time ago, what is an ampere? comes very close to that question. Well, an ampere is actually the amount of current going through a conductor, which is a tub right here, filled with an electrolyte. It could be salt water or could be HO2SO4, sulfuric acid, and you have a silver spoon here as an anode and a cathode over here. So when you put electricity through it, the energy wants to travel from the cathode to the anode through the water. And during that process, it will take away a little bit of silver and it deposit it on the other side. So 1 ampere is deposits of 0.00185 milligrams of silver from point A to point B. That's the 1 ampere during that very same stage. So it can take on water as a conductor in a way to pass on electricity. Matter of fact, I don't think I can explain it better than this example. Let's look at the spider as an example. The spider consumes food, and what it does with the food, it makes a web. And the web is so powerful that it supports itself, and it will not even, if a fly flies in, it still sticks to it. So there is a process of making a finished product at low temperature. Modern man needs to do that too. So the idea is, if I want to make an engine block, as an example, how would I do it? I would make a cast out of wood, paint it with a metallic paint, put it in the water, put electric current in it, and within 3 or 4 days I have an engine block, because there are a lot of minerals in the water, and through the cathode and anode, it will transfer the amount of minerals in the water onto my mold, and then I have a finished block. So here we are. I don't have to melt steel, but through an electrolysis process, I can make anything, literally. So this technique needs to be followed out, and we learned it from the spider. So what we need to do is, it's called nanotechnology. Modern man should not fiddle around with a cell phone all day long. We need to generate a lot of engineers, and the more we have, we can save mankind. A lot of things what we're consuming are using high energy temperatures and a melting point of burning coal and electricity unnecessary. So methods have to change, and we're in the middle of, you need leadership, and the leadership isn't here. Hardly anybody nowadays, or a very small portion of children go to college nowadays. They don't get married, they have no children, they have dogs instead. There's something wrong with the way we're doing things, and I hope that over time we learn from what's happening in Europe. Matter of fact, because Sid and I come here now for 45 years already to Ashland in the winter time, then we leave again. We're blessed with the amount of knowledge we have here, and we bring knowledge into the community. We take some out. So there is cross-fertilization occurring. Field. Go ahead.
Well, so a movement of electrons. So does that mean, like if I'm running electricity through this wire for 1,000 miles, that there's electrons moving from one end to the other? Or is it more like an energy wave that, like it hits the end and you feel it at the other end immediately?
Yeah, it's a domino effect. It's not moving, but it's pushing.
Right.
And then the next one's pushing the next one. And
Right.
it goes at the speed of light, which is 300,000 kilometers per second,
Right.
or 186,000 miles per hour
Okay, that makes sense.
per second.
But then you said if you had 2 silver spoons that were conducting electricity through a reservoir of
Yeah.
salt water or whatever.
Yeah, H2SO4.
that a little bit of silver from this spoon is being transferred to this one. So my question is, over time, will this spoon disappear and this
Yes,
one
it would.
twice as big?
Exactly. The more current goes through it over a long period, the spoon will disappear, and it has a coating of silver on this other item which you have. And that's exactly the same principle of making an engine block or any other item you would want to make, you know. So you're putting an electrical current flows through it, and it will deposit, and it's very strong. Matter of fact, items in an engine block have a camshaft, and a camshaft which lifts the valves up and down. the camshaft has to be very, very strong, and it is through a special process of electroplating that it makes it hard. Many of the shovels which are used for digging out tar sand in Canada, as an example, are from going into the soil and moving it. The friction wears off the steel, and they have to hire welders who weld the bucket day after day to build up that iron that just lasts during the process of moving it away. So I will come back to this issue of the electrical energy one more time. How do we do it? Well, in Switzerland, and in the tunnels underground, 1 or 2 kilometers or 1.5 miles, there's a tunnel. And a tunnel was built in 1962. It is a very cold temperature, over 400 minus, where it is called an accelerator, where electrons, protons, and neutrons are shot. And it was in 1962 that they finished the project, and they're doing still some research in it. And it is still not quite complete with the job. So what has happened is that in the United States, they were busy with that very same project on a much larger scale. So they have a tunnel in Chicago, which is 17 kilometers or 27 miles in diameter, and it makes a circumference of it's called an accelerator. I have a little card here on that subject. It's called a collider. It's in Chicago, Trevaton, and it has 128 tons of liquid hydrogen to lower the temperature for this underground tunnel. And what they're wanting to do is to bombard the electrons. They study it very carefully. So they want these electrons to travel at the speed of light and still take information. In 1 second, it can make 11,200 laps in that circle, which is 82 kilometers, one loop by itself. So the magnetic field is so powerful that over 1 trillion volts are being generated during that time. And so much data is collected that we can fill that information on 3 million DVDs. That's occurring only in 1 second. So man is not finished doing research in that particular field. We need to know more to this point. Go ahead.
Go ahead. Yeah. I believe that Tesla had a way of transmitting electricity without wires, and the problem was that you wouldn't be able to charge for the electricity that was generated. Could you comment on that? Do you have any idea how that works?
Yeah. Our frequency, we call it ether. That's what they call it in Europe, ether. It's loaded with so many frequencies. Long time ago, we used to have the Titanic. And in order to send a signal from the Titanic to either to London or New York, what happened is they had a generator on the ship which had brushes, and the brushes make a certain amount of interference. And then a Morse code was sent over it. All the frequency. One ship was so powerful with its frequencies that it was spread all over the place, and you could pick.
So it would be like keying a mic on a CB radio. So you were interrupting that signal by keying the mic. Does that make sense? Or operating that telegraph key.
So that's just an electromagnetic wave.
Yeah. So
it's not conducting.
It's in the ether, and it carries it. The brushes of the generator make that kind of a sparking, and it takes up a lot of space in the area. We have now so many more satellites in outer space. We have cell phones, we have shortwave radio, all kinds of frequencies, including smart meters for water, gas, and electric. And we are loaded with it, and it's also called cancer causing. the industry is very much aware of it and they want to hush it up. In fact, Motorola is one of the most negative in the whole deal of making that energy. So Tesla's methodology would be sending energy into the grid and then you pick it up at other areas. He still has to produce electric power. When he went into bankruptcy, that is Tesla, I looked at the equipment which went out for auction. It was an enormous amount of generators and motors and equipment and transformers which we had. He was financed by JP Morgan and by Westinghouse. So what I was saying is he had this large spear and a tower where the energy would go in. And I had a friend in Canada, Ernie Vertman, had an employee with him, and he made the Tesla coil. And what he did is plugged it in with a 120 volt outlet, and he had a very high voltage. There were fluorescent lights turned off on the ceiling, and when this unit was plugged in, the fluorescent lights were illuminated. So there's an energy in the room, I call it the ether, and it picked it up, and the fluorescent light was shining because there's mercury in it, and the mercury atoms are making
Activated.
So then there was no way to turn the lights off, right?
That's right. You have to unplug the unit, and then the light goes out. So what I'm saying is that you're filling the air with frequencies, and in many incidents they are unhealthy. We have now found out that it causes cancer.
But on the same basis, if you go to the dead Indian high voltage lines that come over from Klamath, and you hold up a fluorescent tube, you can get it to illuminate just by standing under the...
Yeah.
Really?
Michael McGuire, a communication engineer which was on our board with Green Energy Wind Power, he said he had one nail in one hand and he plugged it into the ground, and he had a little wire on a light emitting diode, an LED, and another piece of wire this long under a high voltage line, and the LED light is shining right away. So what he wants to emphasize was that there is energy in the area, and it makes the light bulb work.
So if you built a little house underneath the power lines, you can just have good free.
You could. There was one guy in Germany who was near a radio station, and his eavesdropping picked up that energy, and the company could not figure out why they would not reach with their calculations further away from Berlin to reach other trends. He used it for heating his house, and it was the eavesdropping that picked it up. It comes back to the whole idea, if you see an airplane up there with a headlight on, the question is, how long will that light shine in that airplane? Till the fuel runs out, till the tank is empty, and then the light will go off. And so there is something to be a good Samaritan, to conserve a little bit so that our next generation has something. Why do you think we have that lady in Sweden, Greta Thunberg?
Yeah.
As a student, it's their lives, it's their future. They're going to inherit the planet, and look at the things we have done ourselves. So by having built my own electric car in 1970, which is a long time ago, that's 50 years now, if I could go one step further on that car itself, right now we have over 1 billion cars on planet Earth. And if somebody looks into the crystal ball, they would say, yes, in a few years there will be more and more cars on the planet. And wouldn't it be nice, rather than crushing 1 billion cars because we're going to go with the electric car, wouldn't it be nice to convert them? So the engineer, which you have from time to time within our own company, he calls it Revolt. The hardware is available that you can build an electric car like this gentleman did here. It's a 1966 June Popular Mechanics on page 27. He made it out of plywood, and he built this car with 6-volt batteries. And it's a runnable car. So what I'm saying basically is the vehicles we have today could be converted if we have the interest, cottage industry. I can convert any car into an electric car. I can get the generator, the starter, the batteries, the wires, the electronic equipment that goes along with it. Here's a typical example of an American citizen who lives in Ashland. He's an electrical engineer. Brad is his name. He's a member of SOHIVA, the Southern Oregon Electrical Vehicle Association. He has a photovoltaic on a Volkswagen. He has a Volkswagen engine removed and an electric motor installed. It's off on the shelf. And what he does with his family, he only travels 50 kilometers every day, every third day, only after the sun is down. So here's what is happening. Pay attention. He's moving from one campground to another one. He stays for 3 days in one campground with his wife and children. And the roof is up and the sun is shining, charging the batteries. And then on the third day, he's driving 50 kilometers or 50 miles to another campground with the energy from the sun. So there you are, you're self-sufficient, done by a local electrical engineer in this valley right here. And you have Susie off the Heide, who drives an electric car, electric truck, and here she is, and here's the truck. And it is one of the only ones left. It's registered under the motor vehicle branch under motorcycle unit. There's Susie off the Heide is on there too. And here's the car.
How far could the electric car from the early 1900s go?
Well, you see, it's not necessarily confidential. Here's the whole thing. In North America, even in Germany too, every household pretty well has 2 cars or maybe 3 cars. One car could be used for the highway, but the other one, this other vehicle I have here is a runabout. With that one, you can go shopping just like the way Susie off the Heide does it. You can go from here to the grocery store, to the bank, or to the church. And the other one, if you're lucky enough to have one a bicycle, other than the bicycle, you can travel with that with a friend by sharing cars to another area. And so the whole idea of something strictly utility, that's what Susie has, is a typical example as to the way we go. Don't ask the question the way you ask it, how far can you go with that car in 1913? Probably 12 kilometers or 12 or 14 miles, you know. But that's satisfying for those who are crippled, who haven't got the legs to do it with. And that's a fringe benefit, Bramo is another motorcycle manufacturer made in this country, right here in Ashland. It runs on electric batteries also, locally made right here. The police had promised they would buy them. The local police in Ashland, and they haven't. I've not seen it yet. Bramo,
Yeah.
beautiful.
That's a bike, isn't it?
It's a motorcycle, and there's a recharging station on top of the hill at Green Springs. 2 stations to plug in. There was a sales dealer on the car which Susie off the Heide, it was in Grants Pass. There was a sales dealer selling those cars which Susie drives. There it is,
Oh, yeah.
Grants Pass.
That guy was a thought.
Yeah.
He was pretty interesting. I liked him.
Okay.
He sold those vacuum.
Here's another electric car. It was built, also homemade, electric car, another example of, it is within our means that can be built. There's no secret behind it. Any electrician or carpenter can build it.
So these electric examples that you're showing, how did you charge them? Most people plug it into the grid at their house, right?
Exactly.
Yeah. Are you knowledgeable about hydrogen cells or using hydrogen and either to produce electricity or to replace fuel as, like I read about one guy that, or I saw it on the internet, that he was burning hydrogen. He was doing electrolysis, splitting the hydrogen and actually burning that in an internal combustion engine.
And then
And
putting
supposedly
out
just
water.
gave off water.
That's correct.
Yeah.
Out the exhaust.
So, yeah, but you don't hear
It
much
takes a
about
lot
it.
of energy to split.
Yeah, you need electric energy to begin with to make electrolysis.
Right.
And then the storage is difficult. The latest research shows that you put feathers from a chicken into the gas tank and then you can fill it without problems. You cannot just put hydrogen under pressure in a tank, it doesn't work. There has to be something else in it, and they found out that chicken feathers are the best technique. Sid wants to maybe add a little bit.
What Toyota's doing is they're creating the electrolysis and then burning it, and there's no storage. So you separate the oxygen and the hydrogen and you consume it immediately. And so there's no tank or storage phase There's electrolysis and the consumption or burning of it
So
immediately.
you put water in your gas tank,
And, okay,
electrolysis, and can you get enough photovoltaic electricity to do that and go down the road? Like in,
I think it's just a hydrogen, I don't think it's a hybrid, the way Toyota's doing it. But I think.
so they're burning hydrogen in the internal combustion?
That's my
Yes,
understanding.
yes.
But I think is, what my father was describing, BMW had done some experiments, and I guess hydrogen is a very difficult to store.
Yeah.
Yeah.
And they're very explosive,
Correct, yeah.
potentially dangerous.
Yeah,
At the end of the Second World War, there was a shortage of gasoline, but there were still many vehicles on the road which needed to bring in food and equipment for the citizens of Berlin. When I was living there, there was a new invention done by a German engineer who actually put an extra tank at the back of the and there was ship wood in it, and there was a fire underneath, and what he did, he boiled the wood, and it created a wood gas, and he ran the engine. So you started with gasoline, and then you open up the valve, and then you run it on wood gas generated in the car. Lots of trucks and cars in Berlin were run because the fuel was needed for the military, and so the local public found a way to do it. And now when the forest is at stake, you wouldn't want to do it, but there's another way of doing it. You can do it with a flywheel running in a vacuum. The French people have been doing that. A very large flywheel in a car, in a vacuum, and then that energy goes onto your wheels. And you can go quite far, 100 kilometers with it. That's another, but you accelerate the flywheel in your residence, where you have an electric outlet, and that spins at several thousand RPMs, and then with that high speed flywheel, you can drive. Very simple, very simple.
Is a flywheel like a fan? What's a flywheel?
Flywheel is a large, could be about 300 pounds in weight. It is on an axle, which is a ball bearing in it, this high and this wide, and you spin it in your own residence. It takes over an hour to get it up. It's like an ultra centrifuge, really high speed. And then you unplug it, and then when you want to drive it, you put it in automatic in the shift, the gear,
You have gears, yeah. Right.
and you can go. So that's another way of doing that. Many methods, and I kept saying that in India and in China together, there's over almost 3 billion people there. Every day new ideas come forward, and those ideas need to be implemented. When the radio was first invented, it took 25 to 30 years before they were mass produced. And I have a list of the items, everything what we've done, including the zipper. It takes so many years before it's ready for mass production. Anything comes up now, within 1 week, it's already mass produced. So the time duration is shorter and shorter, which is a fringe benefit to us. And as we all know, in China, it's reverse engineering. They make so many things over there, they don't pay any attention of who had made them before, and they bring them over here and we buy it for a little bit less. But that's a different story all by itself.
Politics again, Gerry.
My daughter drives a car, and I think she was very proud that hers was a hybrid. But I will show you now a picture of what a hybrid actually looks like. A hybrid has an engine on one side, and it has an electric motor. And the electric motor can only run when the engine puts sufficient energy out to store it. And I'll show you what a car nowadays looks like, which is a hybrid. There's the engine and there's the electric motor, a very complicated thing. And I'm not trying to pick bones with you on the subject. So a hybrid is not necessarily the efficient vehicle to travel with. You're better off to use what they did in 1913 with the Baker car, getting the electric energy from the sun into the battery and then drive it. And there's a motor in it which has an armature and brushes. Something very, very simple and straightforward. Instead,
Cars in New York City at the same time didn't have batteries. And I thought that was super curious, but I only read it in one place one time, so.
Well, Susie's car has lead acid batteries, and they're not so explosive as the nickel cadmium has, or even the lithium ion battery is. There are at times where there's a failure and then there's a fire as a result. There's nothing wrong with really a lead acid battery. It's just it's heavier. One of the drawbacks.
Lead.
Why do you think the gas mileage has not been more improved over the years?
Okay, I want to explain that to you. There are occasionally improved carburetor where you can make a longer distance with the energy going in. There are so many parts. It requires an electrical spark, it requires the fuel, and it requires oxygen. And no matter how you do it, even with the latest improvement in the carburetor, you get only 15% of energy from the fuel going in on the road, on the tires. There's also friction losses due to the air you're pushing, and I notice the windshields are now very flat. And there's road resistance too on the tires. Rudolf Diesel came along, and he doesn't use an ignition system. The fuel is burned under pressure, and it's 2% better than the internal combustion engine. So the diesel engine is actually much more efficient. And what I have been doing, I drive a Volvo with my son. It was from 1980, which is 45 years old, and I got over 450,000 kilometers on it. And I drive it on vegetable oil. So what other people put in their dumpster, I re-refine it myself, and I add a spoonful of lime with it to change the molecular structure of it, and I have a fuel which is compatible to the engine. So there are ways that we could, instead of having that fuel go to the landfill site or being dumped, it can be reused in a better way. But then you have to have patience, you see, and you have to have the time to do it with. We got 5 minutes to go, and I want to speak for a brief period what I had left off when I talked about spiders. We can melt steel using electric power. And what this picture is done in France. The sun shines on a whole series of mirrors, and the mirrors are realigned to shine on a central point on top of a small tower. The energy from the sun is so intense at that point that they can melt steel. So there is a way that, just like that other gentleman creating steam to run a printing press using the sun, we can do it with steel also. So if we have our politicians to work on the soft pass, something what Emily Lovins had been talking about for many years from the Massachusetts Institute of Technology. Emily Lovins believed in Rocky Mountain Institute. So there are ways that we can reduce our footprint on planet Earth and still have a happy life.
Thank you so much, Gerry.